Base brake systems enable a vehicle to stop in a controlled manner. These systems use friction to convert motion into heat. The heat generated is in proportion to a vehicle's speed and stopping rate. This means that higher speeds and faster stops generate more heat. When brakes get too hot, they will fade and lose a significant amount of their stopping ability. This course divides the brake system into the subsystems shown here. It does not cover the anti-lock brake system components. Click each subsystem to learn more about it. The main components of the Apply system include the brake pedal linkage, and the power brake booster. Pressing the brake pedal activates the linkage, which connects to the brake booster. The brake booster eases pedal effort. The brake stop lamp system includes the brake switch, the wiring, and the brake stop lamps. The brake switch is normally located on the brake pedal linkage, where it signals brake application to vehicles following behind. When pressure is applied to the brake pedal, the switch contacts close, the circuit completes, and voltage is applied, illuminating the brake stop lamps. Typically, the brake hydraulic system consists of the master cylinder, hydraulic lines and hoses, and the combination, proportioning, or metering valve. It also contains disc brake calipers and drum brake wheel cylinders. The hydraulic system is split into two independent circuits for safe braking. The hydraulic system is effective because it transmits and multiplies braking force for effective braking action. Vehicle brakes are fitted on the front and rear axle hubs. There are two types of wheel brakes, disc brakes and drum brakes. Although both brake systems rely on the same basic principles to slow a vehicle, disc brakes are more commonly used. Disc brakes cool quicker, use fewer moving parts, and are more efficient. In a vehicle with a combination of disc and drum brakes, the disc brakes are placed on the front wheels while the drum brakes are positioned in the rear. Hydraulic lines connect the brake at each wheel to the master cylinder. Click each tab on the bottom of the page in sequence to view the braking operation for a vehicle with disc and drum brakes. To begin, click on tab 1. Braking action begins as soon as the driver pushes the brake pedal. As a result of the driver's action, the linkage connected to the brake pedal moves the brake booster push rod. The brake booster multiplies pedal force. This increased force helps move the valve in the master cylinder. As the valve or piston in the master cylinder moves forward, brake fluid moves out through the steel brake lines and hoses to the front and rear brake components. The balance control system enables a balanced application of the brakes, with the front brake system performing a greater percentage of the braking activity. As the rear drum brakes apply, the wheel cylinder pistons overcome spring tension to force brake shoes against the spinning drum. When the front disc brakes apply, hydraulic fluid moves the caliper pistons and squeezes the brake pads against the spinning rotor. Many new vehicles have a four-wheel disc brake system. There are several advantages for using disc brakes over drum brakes. Disc brakes provide quicker cooling, which increases their effectiveness and also dissipates water better due to their open design. The overall base brake system on vehicles with disc brakes on all four wheels is very similar to those with front disc and rear drum brakes. On four-wheel disc brakes, the rear brakes apply slightly before the front. On all four wheels, hydraulic fluid moves the caliper piston, which squeezes the brake pads against the spinning rotor, slowing or stopping the vehicle. To review, in a single-circuit hydraulic system, a loss of pressure results in complete loss of braking. For safety purposes, since 1967, most vehicles have had two independent hydraulic systems connected to the wheel brakes. The presence of two independent hydraulic systems ensures that the vehicle is able to maintain some braking operation even if there is a loss of pressure in one of the systems. There are two types of dual hydraulic circuits, front to rear and diagonally split. The front-to-rear hydraulic split system is the older of the two split hydraulic systems. In this system, one outlet from the master cylinder is connected to a line going to the two rear brakes. The other outlet from the master cylinder goes to a line that leads to the two front brakes. This system is only present on rear-wheel drive vehicles. There's a disadvantage to the front-to-rear hydraulic split system if there's a brake system failure. The front brake system performs the majority of the braking activity, and the rear brake system undertakes the remaining portion of braking. If the front brake hydraulic circuit fails, less than 50% braking capability remains. Therefore, if the front brake system fails, significantly greater pedal effort will be required to stop the vehicle. Today, all front-wheel drive vehicles have a diagonally split hydraulic base brake system. In this configuration, the brake lines are arranged diagonally with one outlet from the master cylinder connected to a fluid line going to the left front and right rear brakes. The other outlet from the master cylinder goes to the fluid line that leads to the right front and the left rear brakes. The diagonally split hydraulic system equally balances the braking effort of each hydraulic circuit if one fails. In situations where the brakes of one diagonal circuit fail, 50% braking capability remains regardless of which circuit fails. Most vehicles use hydraulic brakes. All hydraulic braking systems use brake fluid which is specially formulated for the brake system. Brake fluid is not compressible, meaning it transmits force to various braking system components when the brake pedal is pressed. Brake fluid must remain stable over a wide temperature range in order to maintain a properly operating braking system. Typically, these fluids have a high boiling point, over 400 degrees Fahrenheit, that's 204 degrees centigrade, and a low freezing point down to minus 50 degrees Fahrenheit, or minus 45.56 degrees centigrade. A great deal of heat is generated during the braking operation. This heat enters the hydraulic system. Brake fluid must not boil and transform into vapor, because vapor does not transmit motion and pressure or force the way liquid does. If the brake fluid boils and turns into a vapor, the brake system will fail. Therefore, brake fluids must have a high boiling point. The brake fluid must have a low freezing point. If the brake fluid thickens when it's exposed to cold temperatures, it will not transmit the pressure from the brake pedal properly, and the brakes will not function as intended. Brake fluids come into contact with a number of parts. They must not corrode metal or deteriorate rubber brake components such as the cylinder pistons and seals. In fact, the fluid should be able to lubricate those components. Brake fluids inherently absorb moisture while in the hydraulic system. Because of this, two boiling points are listed for brake fluid. The dry boiling point indicates the boiling point of the brake fluid without moisture. The wet boiling point indicates the boiling point of brake fluid with moisture. The wet boiling point is always lower than the dry boiling point. The exact amount of water allowed in brake fluid and how the boiling points are determined are covered in standards issued by the Society of Automotive Engineers, or SAE, Standard J1703, and Federal Motor Vehicle Safety Standard, or FMVSS 116. The fluids are normally referred to by their Department of Transportation or DOT numbers. The primary types of brake fluid are .3, .4, .5, and .5.1. Click on each button to learn more about the fluid. .3 brake fluid is a natural polyglycol brake fluid. It ranges in color from clear to light amber. It absorbs moisture from the air. The dry boiling point is about 401 degrees Fahrenheit, while the wet boiling point is about 284 degrees Fahrenheit. It's used in most domestic vehicles and almost half of imported vehicles. .3 can damage interior and exterior automotive paint finishes. Like .3, .4 brake fluid is a natural polyglycol brake fluid that ranges from clear to light amber. It absorbs moisture from the air. The dry boiling point is about 446 degrees Fahrenheit, and the wet boiling point is about 311 degrees Fahrenheit. It maintains a higher boiling point than .3 fluid. It's used in many domestic and imported vehicles. .4 can damage interior and exterior automotive paint finishes. .5 brake fluid is a synthetic silicone brake fluid. It has a purplish appearance. It does not absorb moisture from the air. .5 fluid's dry boiling point is about 500 degrees Fahrenheit, and the wet boiling point is about 356 degrees Fahrenheit. It's non-corrosive to hydraulic system components and does not damage automotive paint finishes. However, it does have a few undesirable properties. It compresses slightly under pressure and thus causes a spongy brake pedal feel. It also retains more air compared to .3, 4, and 5.1 fluids, which leads to performance problems similar to those caused by vaporized brake fluid. .5.1 brake fluid is a synthetic, non-silicone polyglycol-based brake fluid designed specifically for anti-locking brake systems. .5.1 is typically used in severe-duty and high-performance vehicles. It's clear to light amber in color. .5.1 is hygroscopic, so it absorbs moisture. Its dry boiling point is about 500 degrees Fahrenheit, and wet boiling point is about 356 degrees Fahrenheit. .5.1 can be expensive and difficult to find. It's important to note that .5.1 can damage automotive paint finishes. Currently, higher dot numbers indicate higher boiling points. Under ideal conditions, meaning a clean, sealed system, the lower numbered brake fluids last longer. You should never mix silicone and polyglycol brake fluids. .5 will not mix with .3, 4, or 5.1. It will float on top, compromising brake efficiency and possibly causing injuries. Additionally, using .5 in systems designed for .3, 4, or 5.1 can cause the rubber seals to swell, resulting in improper brake operation. Mixing .3 and .4 together will lower the boiling point of the mixture, reducing brake pressure and creating a safety hazard. Are the following statements? Brake pads and shoes have wearable friction elements, meaning they can be worn down by friction. Pads are used on disc brakes and shoes are used on drum brakes. A brake pad is a steel plate with a friction material attached to its surface. Brake pads are found on both sides of the rotor inside the brake calipers of disc brakes. When the brakes are applied, the pads are forced against the rotor surface. This causes friction and stops the vehicle. A brake shoe is made of welded steel backings and a friction material, referred to as lining, mounted to it. During braking, the friction material or linings contact the drums and the resulting friction stops the vehicle. Different types of friction or lining materials are used for the brake pads and shoes. The choice of material depends on factors such as friction area, surface finish, wear rate, and safety hazards. The friction material chosen for brake pads is generally harder than for shoes because the surface is smaller and a higher pressure is used. The edges of the pads in shoes are often beveled on the leading edges to minimize brake squeal. There are 5 types of brake friction or lining materials available. These are organic, semi-metallic, metallic, synthetic, and ceramic. Click on each type of friction material to learn more about it. Organic linings consist of non-metallic fibers bonded together to form a composite friction material. This type of lining wears faster than some of the other types, but is more effective as a braking agent. Organic lining was typically made of asbestos. Due to health hazards, asbestos has been replaced with other materials. Semi-metallic linings are an equal mixture of non-asbestos organic or synthetic fibers and metal, generally iron, steel, and occasionally copper. Semi-metallic linings are harder and more fade-resistant compared to organic materials. However, semi-metallic materials require higher brake pedal pressure. Semi-metallics are generally used on front disc brakes on passenger vehicles and light trucks. Metallic linings consist of powdered metal formed into blocks by heat and pressure. They are fade-resistant but require high brake pedal pressure. Synthetic linings consist of non-organic, non-metallic, and non-asbestos materials. Fiberglass and aramid fibers are generally used for synthetic linings. Fiberglass is primarily used on rear drum brake linings. Aramid fibers are 5 times stronger than steel and weigh half as much as fiberglass. Ceramic linings consist of a combination of ceramic materials and copper. Ceramic linings are quiet, less damaging to the rotor, and fade-resistant. Today, ceramics are often the brake pad of choice. To review match. A riveted lining is attached to the steel pad or shoe by copper or steel rivets. It provides flexibility between the pad and the lining, absorbing vibration and reducing noise. Rivets provide a reliable and secure attachment at high temperature and mileage. The rivet head can reduce the pad's service life. Also, holes above the rivet head can bring in abrasive materials, which may score the rotor. In bonded attachment, the friction material is attached to the brake pad or shoe with high strength and high temperature adhesive. There is more material between the steel pad or shoe and the drum, allowing the pad to last longer. Because bonded linings do not have the flexibility between the pad and the lining, they are noisier. In mold bonded attachment, heat and a strong adhesive are used to bond the lining to the pad. This method helps to avoid cracking under stress and provides secure pad attachment. Its main disadvantage is cost. Brake rotors are the rotating components of the disc brake system that come in contact with the lining material from the brake pads. The brake rotor is made of cast iron or a composite of cast iron and steel. It's comprised of a hub and a braking surface. The hub is where the wheel mounts. It can contain the wheel bearings. The braking surface is machined on both sides of the rotor. It provides friction surfaces for the brake pads. The side of the rotor where the wheel is mounted is called the outboard side. It's shielded by the wheel. The side towards the center of the vehicle is called the inboard side and is shielded by the sheet metal splash shield. The size of the braking surface depends on the diameter of the rotor. Larger vehicles have larger rotors to accommodate a need for more friction to slow and stop the vehicle. Rotors are either fixed or floating. In a fixed rotor, the hub and the rotor are cast as a single part. A floating rotor is separate from the hub and is also known as a hubless rotor. In a floating rotor, the hub is mounted on the wheel bearings or the axle. The wheel studs are mounted on the hub and pass through the center of the rotor. This arrangement is inexpensive and easily replaceable. In addition to being fixed or floating, rotors can be solid, cross-drilled, ventilated, or unidirectional. Click on the tabs to learn more about rotor types. Solid rotors consist of a solid metallic piece with friction or braking surface on both sides. They're light, cheap, and easily manufactured. They have less cooling capacity, so they are generally used on small cars that need moderate performance or on vehicles with rear disc brakes. For cross-drilled rotors, holes are drilled through the braking surfaces of the solid rotors. This increases the cooling by releasing water and hot gases from the rotor surface. These rotors are light and have short lives and are generally used in racing applications. Ventilated rotors contain cooling fins between the braking surfaces. When the wheel rolls, these fins rotate, circulating air and cooling the brakes. The disadvantages of this system are size and weight. In some ventilated rotors, the cooling fins are curved or at an angle to the center. The fins only work properly when the rotor rotates in one direction. These rotors cannot be interchanged from left to right. The fins must point forward when viewed from above. The brake drum is the rotating component of drum brake systems. It comes in contact with the lining material of the brake shoes. The brake drum is made of cast iron or a composite of cast iron and steel. Iron must be used as the friction surface because of the amount of wear, friction, and heat encountered during braking. A solid cast iron drum is a one-piece iron casting. It has excellent wear and friction characteristics. It's easy to machine and is good at absorbing and dissipating heat. Solid cast iron drums are heavy and brittle. They may crack when overheated. Steel and iron drums are also called composite drums. These drums are light and less expensive to manufacture. However, they are less able to absorb and dissipate heat and less resistant to brake fade. They're generally used on rear drum brakes of small cars. A lubricant is generally used between two moving surfaces to reduce the friction and wear between them. In the braking system, brake lubricants are used when brake pads and shoes are replaced. Lubricants are available in various forms such as liquid, solid, and powder, and in different types including oil and grease. However, in the case of brakes, only brake caliper grease or approved dielectric grease should be used. Brake lubricants can be applied on both disc brakes and drum brakes. In disc brakes, it should be applied on caliper slides and contact points. In drum brakes, the lubricant should be applied on the flat spots on the backing plate. The brake shoe or other moving components may come into contact with these spots. When applying brake lubricants, be careful about the amount of lubricant used. It should be used sparingly, but enough should be used to coat the area on which it is being applied.